Hi, guys.
This is the University of Illinois at Chicago. This is Lee Merrick.
How you doing, Mike?
Good to see you.
And you are?
Peter.
Peter.
Yes.
You're here today because of, you've been under a little pressure?
Yeah, supposedly, yeah.
Okay. And I understand you did an experiment before you came here that involved a smaller can?
We had a smaller can, which we crushed. This looks much scarier.
It is kind of scarier. Yeah.
We saw it with a small can. We thought maybe we could see it with a much larger can.
Yeah, and so we've got some water droplets coming out. That's not steam. That's a colloidal dispersion of water droplets. Steam would be colorless.
No, you lost me already.
All right. See, those are like little raindrops coming out of that can.
Mm-hmm. Okay.
Steam itself you wouldn't be able to see, but that's inside the can. Now, you turned yours upside down in cold water. We're going to do something like that here. We're going to seal this up, okay? Mike and I are going to seal this up with this big honking tool right here.
Yeah.
And after we get it sealed, we're going to take it off the stove, because if we left it on, that would be very unpleasant. So I'm going to see if you grab that tool.
All right, you got started?
Yeah, that's the hard part. We got to get it started while the steam's coming out.
And a good seal, too.
I need to get a good seal, otherwise it's most unpleasant. I think it's time to take it off, Mike.
Okay,
Take it off. Otherwise it's a different experiment.
Yeah.
Okay, now.
Pressure inside.
Pressure inside. There we go. Torque that puppy down.
It feels tight.
Okay. Now, put your goggles on. You got them on? Put your earplugs in and put your ear protectors on. So, when that can was open to the atmosphere a few minutes ago, what happened is the pressure on the inside and the outside were the same. That pressure is about 14.7 pounds per square inch, equivalent to the bowling ball that you guys had before. Every square inch of this can has 14.7 pounds pushing down on it.
Whoa.
Right now we've sealed it up. So what's happening inside here, Peter, is the steam is condensing. It's turning into a liquid, and there's no air to take its place. So those 14.7 pounds on every square inch of the can are starting to press down. Now, you could actually figure out how much pressure this is if you were mathematically reclined. That is, this is about 23 inches. This is about 36 inches. You could figure out the surface area of this can and how much pressure is on there. You can see the top is a little bowed already. So to speed this up, we're going to add a little bit of dry ice to cool it down. And we'll add a little bit of wet ice with some water.
That looks cool.
Or we're trying to cool it down faster, right?
This is going to make it cool down faster. This will take a while for it to condense and the air pressure to make the can. It won't be as fast as the one that you did the other day. So we're just going to sit here and wait, and we're going to see what happens. I've had people give me...
Oh, wow.
You all right, Peter?
Okay, just
You look a little wet, Mike.
Oh, boy.
that was awesome.
What's actually responsible for this having happened?
Well, on each square inch of that can, that 14.7 pounds,
This bowling ball right
this
here.
bowling ball is pushing down on each square inch of that can, and that outside pressure squashed it because the inside pressure was pretty close, but not exactly zero. There was still some air and some water vapor in there, but it's pretty close to being zero pressure on the inside and the outside. You can do that calculation in the privacy of your own home.
So low pressure inside the can.
Correct.
And just normal room temperature pressure pushed in this can and made it pop like that.
Exactly.
Still going.
Just like your can.
I mean, I don't feel like I'm being crushed with the same air pressure that this got crushed with.
You know, Mike, we could do that to you. If
Please
we had a
don't.
vacuum pump, we could put that hose into your mouth, seal your nose, and if we pull that air out of your system,
Yeah.
you would collapse like this can.
Let's do that next time.
To Peter, we don't want to do that.
Okay. Well, thanks a lot for showing us this. This
Appreciate
was great.
it. Thank you.
Thank
Hope you
you.
got
That
something
was-
out of it, Peter.
I got wet. Hope you got something. Thanks a lot.
Okay, take care.
So I'm beginning to see that air pressure has something to do with my door problem.
Yeah, I hope your bet wasn't a very big one.
Doesn't matter now. So what's this?
This is the exact same demonstration you saw before, but I'm going to show you something a little different.
This should be interesting.
Okay, so what I have here are two liquids. One is blue, one is clear, and over there in that flask.
Water in the bottom, which is being heated and turning into steam.
Sounds like you've heard this before.
I'm just saying that I learned.
Okay, so put your glasses on. And if you would please get the lights, I think you're going to like this. Okay, you ready? Watch carefully.
Oh, cool, it's glowing.
That's right. Okay, go on and get the lights again. Did you see what happened?
Yeah, those two liquids got sucked up.
You see, that's where you're wrong. Science doesn't suck. They got pushed up.
By air pressure.
That's right. Let's see how. Like other things we've seen, the container was filled with hot steam. When it cooled down, it created a vacuum, a low-pressure space inside the container. High-pressure air outside pushed the liquids inside. When they mixed, a reaction took place, and they glow.
But it didn't suck.
No, science never sucks. That's very important.
I'm beginning to see that when you have a high pressure, you have a lot of gas, and when you have very low pressure, you have very little or no gas.
Yes, yes. That's called Avogadro's law, and it works a lot like Charles' law. Pressure and the amount of gas go up and down together.
I can see that now.
Good. Now let's look at some pressure and volume relationships. To review, volume is the amount of space something takes up, and pressure is the amount of force a gas exerts on a certain area. Let's imagine a gas inside a container with a large volume. Each of the particles is moving around, bouncing off the walls of the container and each other. Now let's start making that container smaller. That makes the volume go down. Look at how those particles are moving now. They're hitting off the walls more often and hitting each other a little harder. The smaller it gets, the more the pressure builds up. And the larger it gets, the pressure will decrease. This is called Boyle's law. Basically, it states that pressure and volume are inversely proportional. But think about it like this. If pressure and volume were playing on a teeter-totter, every time one went up, the other would go down. When pressure goes up, volume goes down, and vice versa. Now, let's see Boyle's law in action. I've got here a highly scientific piece of equipment. This is a tube. It's hollow, and I can see all of you. This is another highly scientific piece of equipment called a stick. Now, all I'm going to do is I'm going to take this tube and this potato and this knife. A heck of a knife. All right, I'm going to cut off a couple nice slices of potato here and here. This tube, hollow, has potato stuck in one end of the tube. Other end of the tube has potato in it. So I got potato in this end, potato in this end. What's in the middle of the tube? Is there anything in there? Is it empty? I think there might be something in there, and I'll give you a hint. It's all around us.
Air.
Air. This is full of air. And air is a phase of matter. It's a solid. Is it a liquid? No, it's a gas. That's right. So this is full of gas. Okay, there's gas filling the tube from this end all the way to this end. So what I'm going to do is I'm going to take this potato here. I'm going to start pushing it in just a little bit. Okay? Now what's going to happen when I push this potato in a lot? The other end should shoot out. Okay? This is going to be an example of what's called Boyle's law. I'm going to take a step back. And give it a shot. We'll go over in that direction somewhere. It's just a potato. They're very tasty. Ready? In 3, 2, 1. Did you guys hear the little pop? Okay. That's an example of something called Boyle's law of gases. This has a certain volume, and there's a lot of gas in there. We made all that gas take up a very small amount of space, and so the pressure inside there got really, really high. So high that the other potato had to give.